All right, a couple of review pieces as we start to kind of gear up for really digging into our new content here in AP Chemistry. Just wanted to review and refresh a couple of our pieces that are going to be really important for us to be thinking about. These are going to become second nature as we go through our content. A lot of these are coming out of college chemistry, but again, I know it's been a while, and so I wanted to highlight some of these pieces just to keep them fresh, keep them in your mind as we're starting to look at our different chemistry pieces. First piece, just a couple of vocab pieces. I'm going to go pretty quick through this. Feel free to pause it, get them down. You could also follow along with the PowerPoint. It is posted on Canvas for you as well, whichever is best for you. But I'm going to kind of move quick because I think short videos are better for us. First, kind of review metals on the periodic table. We know that they're kind of down to the left of the stair step. They all have similar properties. They're conductive. They've got that luster or shine to them, high melting point, malleable, bend without breaking, ductile. We can pull them into wire. Metals, we think of our metallic substances, should have a pretty good framework for that. We've seen that from Chem 1 as well. Non-metals are up into the right on the periodic table above the stair step. These are kind of the reverse. They're dull. They're usually fragile. They will crumble if you hit them with a hammer. Low melting point. Some of them are gaseous at room temperature. And so just thinking about our properties as we start to look at our different substances, we can start to see those exhibited. Acids, we know that these are substances that always or tend to start with an H out in front. These are substances that will cause things to dissolve or corrode, are corrosive in solution. When we put them into water, they give off that H plus to create what we call the hydronium ion. Remember that hydronium is kind of what we call a water molecule that's picked up that extra hydrogen. Bases are compounds that when they dissolve in water, they release and dissociate, split apart. To dissociate means we split apart and we release hydroxide ions, OH minus ions floating around. Those are the reactive particles of our base. And then a salt is any ionic compound. It's got a cation and an anion, ionic bond, kind of sticking them together. Typically, it's a metal and a non-metal. Not always is it a metal. Sometimes it could be the ammonium, NH41+. But we got to have ions sticking together to make our salts, which we know to be brittle, crystalline in structure, solid at room temperature, and all that stuff. Cool. So just a little bit of review of some of the terms that we're going to be seeing and using as we start to work through our first unit and our chemistry. As we continue to think about our review pieces, make sure, we're going to review this here in just a second, that you memorize your strong acids and your strong bases. We know they're strong because they react strongly. They react strongly because they dissociate 100%. They split apart completely when we put them into water. Not all acids do that. We're going to spend a unit talking about how we can quantify a strong versus a weak acid and what that means for us in our solutions. But we got to know, if we look at an acid, is that a strong or a weak? If it's weak, later on we'll figure out how weak it is. Get your solubility rules. As we start to look at net ionic equations, you need to know, does this ionic substance split apart, dissociate in water, or does it not? We'll review that here in just a second as well. Then just a little bit of general review for some of our general reaction archetypes. Single displacement, that was one element and one compound. This is kind of Chem 1 review, one element, one compound. Switching parts to make one new element and one new compound. Double displacement is two compounds switching out to make two new compounds. Combustion is taking a hydrocarbon in the presence of oxygen, burning it to make CO2 and water. Synthesis, you take your separate parts and you smush them together to make one new thing. Decomposition, you take one big thing and you break it apart into its smaller pieces. Hopefully a little bit of review. Hopefully you've got some examples in your mind or remember doing some of these from some of our previous years, but it's good to kind of go back and refresh these. Solubility rules. I'll admit the mnemonic NAG-SAG is wonderful. It's going to get us through about 98% of what we need for even our AP chemistry material. NAG-SAG, and then there's Castor and PMS. NAG, kind of the nitrates, ammonium group 1, they are always soluble. If you have any compound that has a nitrate group in it, it will always dissolve and dissociate in solution. It always splits apart. Same for our ammoniums. Like if you had, for example, ammonium chloride, that's going to split apart when you put it into water, always soluble. Group 1, anything with that first column on the periodic table, always going to split apart. The SAG, that's your sulfates, your acetates, and your group 17. These are usually always soluble unless, so acetate, always soluble. Sulfates are always soluble unless it's with lead, mercury, silver, calcium, barium, or strontium. That's the PMS Castor. If it, for example, was lead sulfate, that would not be soluble. That would come out as a precipitate that filtered down to the bottom of our flask or our test tube or our beaker, whatever it is we happen to be working in. And then for our group 17, kind of the PMS does double duty here. If you had lead chloride, mercury chloride, or our silver chloride, these are insoluble. They settle out of solution as well. Otherwise, anything else we see should be soluble, so long as it matches our solubility rules. Just again, refresher, as we start to think about kind of prepping for our net ionics, good to remember these. Strong acids and strong bases, I can kind of give you some tips here, but for the acids, you just kind of need to know the strong acids. There's only 7 of them, and some of these you should be fairly familiar with. Hydrochloric acid, you know, is strong. We've used that all the time in chemistry. Dissociates 100% of the time. It is a strong acid. Hydrobromic acid, hydroiodic. These are the 3, we call those the halide acids or the halo acids because they have the halogens in there. And then for our oxo acids, our acids with oxygens, our polyatomic groups, we've got sulfuric acid, nitric acid, perchloric acid, and chloric acid. These are kind of the 7 strong acids. And the reason this is important is if these are reacting, they split apart completely, which usually means for our net ionics, we're just going to have the H plus floating around. We're not going to have to worry about the anion because it's dissociated away. For our bases, there is a shortcut for the bases, which is great. For our strong bases, it's going to be group 1 and Castrobare. So if you have, for example, sodium hydroxide, that's a group 1 with a hydroxide, always strong. Anything in the first group, so lithium hydroxide, potassium hydroxide, all of those are going to be strong acids, strong bases. And then if it's calcium, strontium, or barium hydroxide, those would also be considered strong bases. Magnesium hydroxide is not a strong base. That is a weak base. It stays stuck together when we start to think about our net ionic equations. We're going to review those, do a whole other thing on those. But again, just kind of reviewing some of these important kind of chemical facts that we need to have in our mind as we start to look at our different reactions. Cool. This piece is new. I got to throw this in here because as we start to look at the AP exam, they really like to throw this question in there. This one we haven't heard before. We've kind of mentioned it in passing, but we never really kind of drilled in on it. Noble metals. Hopefully, kind of pings your radar with our noble gases. Noble gases being that they do not react. Noble metals are metals that do not react with our hydro acids. So usually we say metal plus an acid, hydrogen gas, and a salt. But there's a couple acids that don't do that. For example, gold is a great example of this. Gold, one of our noble metals, we use it because it doesn't really corrode. It doesn't really react. It stays as it's gold. It's one of the few metals we can dig up directly from the earth because it doesn't react with our environmental species. We call that a noble metal. So there are kind of 7 of these. I will admit the rhodium, palladium, osmium, and iridium are much, much rarer. You would not typically see those. What you might see in a chemistry lab, I know it seems silly that we would see it, the 2 big ones would be the silver or the platinum. We actually can kind of get those. So we have a couple of platinum electrodes that we'll pull out when we get to our electrochemistry unit. But gold is also kind of one of the big noble metals. And so sometimes you'll see these slipped in. It's like, write a reaction for gold plus an acid, and you want to just make it hydrogen gas and salt. It actually would be no reaction. Gold, it would just sit there. The gold would just settle to the bottom and sit in our reaction chamber. Cool. So just wanted to kind of talk about some of these different kind of key pieces that we got to keep in mind as we start to move forward in our content. Awesome.